This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. So at the end of last week, we derived entropy as a property and determined that my coffee wouldn't unmix itself all by itself, which is a pretty important thermodynamic principle. Today we will go on with some of these definitions and derivations, confirm a couple of things that we've just stated. So we stated last week that a isentropic process is adiabatic and reversible. We're going to show that mathematically, and then at the end of this lecture we'll have a look at a couple of different places where entropy becomes useful in our thermodynamic analysis. So first step, what's a reversible process? What's adiabatic and reversible? What does that look like mathematically? So we've already, just to flash back, we've already introduced the idea of an adiabatic process for an ideal gas. If you remember, we had the polytropic processes and said that PV to the power n equals some constant for an ideal gas, and that if n equals gamma on that guy, that's the process map for an adiabatic process, where gamma is the ratio of Cp and Cv. So it's also called the adiabatic constant. So we've already played around a little bit with adiabatic. We've briefly looked at the idea of isentropic in the sense that there is no change in entropy. And we're going to use those two ideas and join them together and have a look at what happens. But we've also started to throw around this word of reversible. So I indicated as we were introducing the idea of entropy, we were talking about it is our mathematical number that tells us that in a certain change, which way should that change go naturally, and which way, if you want it to go the other way, the not natural way, which way would we need to put work in to make it happen. If we've got no entropy change, that's a nice easy situation. We know that you can go from one to the other. No entropy change doesn't mean no energy change. This is an important one, because an isentropic process is still a process going from one state to another state, and if we're changing states, we're changing energy content. So it's a useful idea. And the core to our reversible process is this idea that I've got no extra losses that I can't keep track of. So we still count the idea of our system surroundings in the sense that I might still count work in this idea. So the statement up there, a reversible process changes the state of a system in such a way that the net change in the combined entropy of the system and its surroundings is zero. So we said that we could have zero change. We also said that we could have positive change. This is the zero change. The reversible is the zero change. And the idea stands in contrast to all real processes, because all real processes have some losses. As soon as you have friction in a process, you have unaccountable, like unretrievable energy losses as something's going on, which is if you were to drive the process the other direction, you would be taking more work, more energy input to get back to your original state than what was released on the way out. Now you can map that out, you can describe that in words, and it seems to make sense, but it also plays through in the concept of entropy and what the entropy changes are between state 1 and state 2. So all physically possible processes are always irreversible to a greater or lesser extent, which leads us to wonder why we're dealing with the idea of a reversible process in the first place. So towards the end of last lecture, we started to build up our tool sets in the same way as for the first law, where we said, I split my world into problems that I'm solving by taking the data from the charts, the tables, and problems I'm solving by using equations. This one is the world of vapor problems, steam, anything that's condensing, so a superheated gas down to a condensing process or a boiling process. And if I'm in this world, I solve my problem by looking at tables. The other world is ideal gases, and if I'm in this world, I don't solve my problem looking at the tables. If I'm in this world of ideal gases, I solve my problem using the ideal gas law and all the derivations that we use to lead to the ideal gas changes in entropy, changes in internal energy, changes in enthalpy. So we've done laws, we've done rules for ideal gas changes in internal energy and enthalpy, and that's where we're using the CV delta T and the CP delta T relationships. At the end of last lesson, at the end of last lecture, we built up also a tool for ideal gas changes in entropy, and we had two versions of them. One was for where I'm dealing with a problem that would be solved with internal energy, and one was for problems where I'd be dealing with enthalpy. So, we showed that we could write, this is the version that's derived for the internal energy. We showed that we could write S2 minus S1 for an ideal gas is CV, the log of the change in temperature, plus the gas constant times the log of the change in specific volume. And that is now in our toolbox. So if I have an ideal gas problem that's requiring me to evaluate the change in entropy, I have an equation, I can plug it in. If I know the two temperatures and the two specific volumes, what if I don't have specific volume? Well, if I know the state, I do have the specific volume. Even if I'm determining my state by temperature and pressure, or temperature and entropy, temperature and enthalpy, or temperature and internal energy, as soon as I have the state pinned down, I also have the specific volume. So if I have two states, I can solve that equation. So we're going to use that and play around with what does that look like. Basically, from that idea, can I get back to the ideal gas adiabatic process, this PV to the gamma, by looking at an isentropic process. So this is almost a little bit of cheating. This is saying I already know where the answer is. Because I've already done this, I know that if I set delta S equals 0, I can manipulate the equation to end up with something that looks like the adiabatic. But let's, rather than me, all these derivations are more engageable if we do them on paper. So let's do this one on paper. That's the tool we're going to use from the previous slide, as well as anything else we're allowed to use. So anything else we're allowed to use by having said it's an ideal gas. So we've already started to build up lots and lots of equations for the moment that I give you the code word it's an ideal gas, you can use any of these. Don't. Okay, good, okay, good. My fear is that I'll get stuck on one screen or the other. They've assured me that they're in the process of fixing these things. What I'm interested in, so I've got this idea of the entropy change, and I've got this phrase that I've uttered that last week that adiabatic and reversible equals isentropic, or isentropic equals adiabatic and reversible. So what we're going to do is, for the ideal gas, we'll take this equation, this S2 minus S1 equals CV T2 on T1. It's a horrible pen for writing neatly. It's bad enough with my handwriting in the first place. So there's our equation. Isentropic is that S2 minus S1 is 0. So if this goes to 0, then I can take one of these guys over and start to play with them. So if we take this guy over, I'll get CV log T2 on T1 equals minus R log V2 on V1. No magic yet, just using the idea that we're isentropic. Then we start to play around. Now, if I get rid of the logs, which is, say, if I take the exponential of these equations, this is the exponent. This guy becomes log T2, sorry, that's the point, I was trying to get rid of the logs. T2 on T1 to the CV. This guy becomes, now what happens to my minus? If I've got a minus in the exponent, I could write this V2 on V1 to the minus R, or I could write this on as V1 on V2 to the R. Just taking the inverse of that statement. Then I'm going to start to use things like the ideal gas law. So the ideal gas law, I've got PV equals RT. What I'm going to do is substitute in, now the direction that I'm heading, before I take the next step, the direction I'm heading is that if I can show, from the statement of entropy equals 0, entropy change equals 0, if I could show the adiabatic relationship equation, this PV to the gamma equals a constant, I've done my job. To get to PV to the gamma equals a constant, at some point I'll need to find a gamma, and gamma is CP on CV, so at some point in there I'll need to find a CP on CV. The other thing is I'll need to get rid of T. So if I want something that says PV to the gamma equals a constant, I need to get rid of these guys. One of my most common ways to get rid of T is to substitute in terms of P and V and R. R is a constant, so I don't really care about it. And P and V are fine because that's my goal. So substituting in for T with the ideal gas law will give me P2 V2 on R, so that's this, R P1 V1 to the CV equals V1 V2 to the R. That bit's okay, that's just the substitution for T2 and the substitution for T1. We're going to cancel out our R's. And what I've got here now is P2 on P1 to the CV, V2 on V1 to the CV. So I'm just grouping up the terms there. And over here, I've got V1 on V2 to the R. So then we're going to play another trick. The other thing that I'm allowed to use, now that I've said I'm in the ideal gas world, my goal, let's just keep here. Goal, show PV to the gamma equals a constant. I don't care what this constant is. So anything, provided everything on one side is a constant, it doesn't really matter what that constant is. So I'm trying to get all my P's and V's over this side and leave constants over the other side. So if I divide through by this, I've got, on this side, I've got P2, let's get the P's down there, P2, P1 to the CV, that's okay. And then my V2 on V1, if I divide through, if I bring this guy over here, it becomes a V2 on V1. And what I've got is CV on R. Sorry, I've got to be careful with that. I've got CV plus R. Yep. So bringing this guy over and then flipping this. So if this is a minus, then this becomes a plus. It becomes CV plus R of this. That's the step that when the first time you see it, you're like, I'm not quite sure I follow that. If you try it by hand, you will find it, which means that this is Cp equals a constant. So I'm almost there. What I now need to do is get rid of this guy, because this was my goal. I had no exponent on the p. So if I take the CVth root of this, which is say, do this on CV, this on CV, Cp on CV, and do the CVth root of the constant. The CVth root of a constant is still a constant. It's just a different constant. So what I get now is P2 on P1, V2 on V1 to the gamma. This was the Cp on Cv. Is gamma now equals a constant. Which is the same as saying P2 V2 gamma is a constant, or P1 V1 gamma is a constant, or just P V to the gamma is a constant. So, a lot of the times when these derivations happen, you get to the so what moment. Do I actually even care? Why did you show me this? Am I going to be examined on it? One of my jobs is to establish that the tools that I wave my hand at and say are real are actually verifiably real. So if I stand and tell you isentropic equals adiabatic and reversible, you accept me at my word because I'm a lecturer and I tell you these things. But the fact that I'm telling you has come from a careful derivation of the ideas and saying, well, look, I've got this idea for adiabatic. We worked out PV to the gamma equals a constant for an ideal gas by saying heat transfer equals 0. We didn't say anything about entropy. So we said that's the way an adiabatic ideal gas works. When I got my entropy relationship and I set entropy change to 0, I say isentropic, I get an adiabatic behavior. So what I've got is an adiabatic and isentropic connection, which is not something that I started off with. Don't get stuck, don't get stuck, don't get stuck. Come on. Thank you. I've decided my new tack is to talk nicely to the computer. Let's see if it behaves. Good. It behaves. Nice. So this is the derivation in text, so you've got the handwriting much neater. That brings up some interesting stuff. That means that we know that isentropic processes have no heat transfer. So isentropic now means for us adiabatic and reversible. If I say adiabatic and reversible, it now means for us isentropic. So we have also a new set of code words that can be used in a question to set out the rules of the problem, how we're going to solve the problem. That's the text of everything I've given to you. Again, this is so that sometimes people hear words better than they read them. Sometimes people read words better than they hear them. So I try to double up. That's a neat result. That closes off some of our sort of derivation and definition of how isentropic works, or functions, let's say. Now let's look at accounting for the losses. We've got an expression for infinitesimal work, dW. When it is boundary work, the system inside a cylinder, for example, dW equals PdV. This only, so we keep being quite careful about how we define which work we're talking about. We keep being careful to talk about it as only the work involved in changing the volume of the cylinder. So that definition of dW equals PdV does not include any extra work that was taken to overcome friction. And quite specifically, the first time we introduce the piston-cylinder equation, we say an ideal piston cylinder with no friction because of this very problem. So it's only considering the force of the piston acting on the system, or vice versa, the system acting on the piston acting on the system, or the system acting on the piston. And so friction is obviously one of them. I've said this in the introduction, that we've got this idea that that's not recoverable. not recoverable in our thermodynamic sense. We can't destroy energy. We know that it has gone from the system. So what not recoverable means is that it's the difference between useful work and not useful work. So when I've got my Q minus W equals change in energy, when I've got that statement around how do I keep track of my energy flows, the work that's in there up until now has been the useful work, the useful network of the system. So we had to work in and work out. If we were doing a cycle, we had some work put in to make it go, some work out, which is the whole point of the machine in the first place. So we have a net work statement, a net useful work. And we have some heat transfer that was required to make that work, and it all balanced nicely. If in my process I have some friction losses, that is not useful work coming out of the system. So we introduced the property diagram, this PV diagram, and said one of its really cool features is that the area under it represents the work done during the process, or the work done, either the work done out or the work done in to make the process happen. That only applies for the reversible part of the process, which means that that PV diagram does not show you what's been lost as friction. And I've said a couple of times this idea of pulling a pulley to lift up a weight. If it's a frictionless pulley, we have the reversible system. The amount of kinetic and potential energy changes exactly balance the amount of work that I put in or the work that came out. And then if I put friction in, I've lost some work from the system, lost some energy from the system. So if there's no friction and accelerations are negligible, then I have this area under the curve. If I go from 1 to 2 at a constant force over a constant distance, force over distance gives me this, which is the area. It gives me the area which is equal to the work of this system. And the potential energy has gone up as I pull it up. And then we jump over to the next side. If I do that again, this is state 1 and state 2. What's missing by drawing the straight line between 1 and 2 is what I had on the previous page. The straight line between 1 and 2 was the reversible process between state 1 and state 2. If there were friction in the pulley, and I pull, I will have to exert a greater force to get it moving, which means that actually my process is occurring at a higher force than the reversible process. And then when I release it, this map is showing me the useful work, or the useful work released by the system. When I release my hands and let the system return work, because the potential energy turning into kinetic energy, etc., or changing its potential energy back to a lower state, I will also lose work and come back on this path. So that's the reversible process backwards and forwards between the two. And the irreversible process is a bit more force is required to make it work, and a bit less work comes out as a result of the friction. Only the stored energy, which is the energy delta between state 1 and state 2, is what can be recovered as useful work, which is why we keep doing these property diagrams. The property diagrams, as we draw them, when we draw nice straight lines between things, aren't picking up those friction losses. And if you were to look at those friction losses, you need to be very, very careful about how you draw your processes. But we have an extra tool now in our toolbox that lets us do this without having to specifically know friction coefficients and the extra delta force and all the little bits and pieces. The entropy tool is our shortcut to all of this. It's our shortcut to having to know the detail of the friction of the system. We've got a toolbox full of isentropic processes. How would a system behave if entropy change was 0? And we have this idea that if entropy change is not 0, my process was not reversible, and therefore there's my map of the losses. So I can compare the losses to the not losses, to the reversible process. So we're going to have a look at those. We're going to have a look at two examples of that, of how we could keep track of these losses, or the changes in entropy. One of them for a compressor, and one of them for expanding gases. The compressor problem that we'll show is, I think, the most common place where you'll find the use of isentropic relationships. So when you learn entropy, and then when you get examined and assessed on entropy concepts, one of the ideas that gets examined is, can you connect entropy to heat transfer, and so can you connect the Q on T idea to entropy? The other idea that gets examined is, can you use the isentropic relationships like these guys, or the ideal gas version of them, to look at the difference between ideal and real behavior. Now, this is an interesting subconscious thing that just happened there. What's interesting to me, as I've said ideal and real, I've done this with my hands, because I've been doing it so many times on a TS diagram where entropy increases for my diagram here. So I've gone like this and this for ideal and real, because this is my isentropic process and this is my real process with entropy increasing, because it's become such a habit of my world of how I think about ideal and real processes. So there's a little nervous tick in there of how do I think. The entropy map, the entry idea, the number that's contained in entropy, gives us our tool for accounting for the losses from the system. It gets us closer and closer to Carnot's idea of what is the maximum amount of work I can get from anything. So, the form of those entropy equations up there is the completely generic, I don't even care whether it's an ideal gas or not, form. We've got versions of those equations now derived for ideal gas as analytic expressions, which means just plug the numbers in and you're correct. We've waved our hands a little bit about this idea of the CV and CP being constant, which means for the moment, the way our equations are written right now are assuming that over the process, I can treat CV and CP as a constant, which is a little flag, so in the future we'll also work out under what situations can't you, and then what do you do if you can't? How big an error do you introduce, and what ways can you minimize that error? So, a lot of my talking already has led up to this idea. These definitions that we derived are only okay for a reversible process. And given that I've also made a statement that all processes are not ideal, all real processes have losses, it begs the question, why on earth would I bother even having these? So, naturally the answer is no, it's not useless. Otherwise I wouldn't bother. The most powerful thing out of this idea of entropy is that it's a property. It's not a process information. So this point number one, I wave my hands to you and I tell you this is really important. You hear and you listen and you go, okay, Rob says it's important, that's great. I'll note that somewhere. I'll put an asterisk on it and highlight it. What I mean is, it's the most simplifying tool or idea to our ability to solve engineering problems. If the idea of entropy were wrapped up in the process, to solve problems of losses, I would need to understand exactly the process that occurred for the real conditions I was analysing. I'd need to know everything about what happened. If I were analysing a car engine, and I wanted to understand the real behaviour of the car engine, I would need to understand the friction in the cylinder at all points during the cycle. So the cylinder's going up and down and it's rubbing up against the walls, and sometimes it's got fresh lubricant, sometimes it doesn't. Sometimes it's got some heat loss that's changing how well the oil is behaving as a lubricant. All of that aspect within the cycle I would need to know for each journey of the piston, if entropy were not a property. Entropy as a property means from point 1 to point 2, I just need to know the states. If I could tell you the temperature and the pressure, I'm telling you the entropy. Which is to say, if the temperature and pressure I measure is not the ideal temperature and pressure, it's the real temperature and pressure, it will be, for example, hotter than what I expected or colder than what I expected, it will be different to the isentropic temperature and pressure. So what we're going to be doing is comparing the difference between what I've measured and what the best possible is, or having some information. If I say I've analysed the compressor and the output temperature is blah, 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 the first thing I would do is say, is that my isentropic expected temperature? So I go on my TS diagram straight up to the new pressure. Hang on, that's a hotter temperature. Something's gone wrong. It is not the ideal process. There's a little magic trick that occurs. Another little magic trick. There's a couple of them in this field. Is this last statement, which is that the entropy change over some irreversible process can actually be mapped as a combo of reversible processes, which is the other reason why the tool is useful. So we'll do that for the steady state. For the steady state, we'll do that for the compression, for the compressor. I like drawing TS diagrams for compressors. I don't know why exactly that I like drawing TS diagrams for compressors. And right now, it's probably a risk trying to turn on... No, the computer's listening. So we've been doing PV diagrams as our property diagrams and saying 1 and 2, chunk. What we're doing now is a TS diagram. Now pay attention while I scribble my diagram down. How many marks have I got so far? In a 2-mark question about please draw the process on a TS diagram. About half a mark already, because I drew some axes and put some arrows on them, and I'm going to get some more marks now. I've got 1 mark out of 2 for my 2-mark question of please draw a TS diagram. If I do that, and the question says please draw the process on a TS diagram, and I go like that, I've lost half a mark or a mark. Just letting you know. Please draw a TS diagram, so I'll draw a TS diagram. I'll put some axes and I'll label them. They're little things, but they matter. On this graph, I'm interested now in a compressor process or a compression process. A compression process could be isentropic or it could be real. We know all processes are real, so let's have a look at what that looks like on a TS diagram. A constant pressure line on a TS diagram kind of does this, kind of does this. So this is P1, this is P2 here. Maybe I'll write it over here. And I start here, which is to say, I start at a well-defined state, 1. My well-defined state only needs 2 things to pin it down. So if I had a magic entropy meter, and I could tell you the entropy, and I also knew I had a thermometer and I could tell you the temperature, that's great. I put it there. What's more likely is I don't have a magic entropy meter, but I have a pressure gauge and a thermometer. My pressure gauge and thermometer define my state, and at that moment it defines my internal energy, my enthalpy, my specific volume, and my entropy. So by knowing this guy and this guy, I know this guy, which also means I know S1. The isentropic process from here wow. Do you know what you do with pens that don't work? You put them right back where you found them so that they won't work for the next person. Do this the rest of your life. It'll drive people mad. I'm on a campaign. I'm on a crusade. Every time I find a non-working pen, I'm grabbing it and throwing it in the bin, and people go, oh, you can't throw that pen in the bin. It came from the whiteboard. Please throw the pens away. Then people will know to get a new pen. It's a little campaign. As you get older, you care about smaller and smaller things. When I was 20, I cared about saving the world. Now I care about running out pens. This is 2. That black line I've just drawn is the isentropic compression. I've moved from one pressure to a higher pressure. So let's say P2 is higher than P1. When I compress a gas, what happens to my temperature? It's on the graph. Is T2 higher, the same as, or lower than T1? There's no trick. T2 is higher. I've compressed my gas isentropically. It's now hotter. I didn't tell you whether it's a vapor or an ideal gas. It doesn't matter. An isentropic compression goes up, changes pressure, because it's a compression, that's its job. Does not change entropy. And then if I were to come back down, I could isentropically expand that gas. That's cool. I can move backwards and forwards here. But let's say, let's give them numbers. Let's say this is 100 and this is 300 Kelvin. Let's say I do that compression. I run my compressor, I put my pressure gauge on, and this was, I don't know, I'm going to make up some numbers, 1 atmosphere and 10 atmospheres. These numbers are not correct. I could do the maths to put down the correct numbers. I'm just putting numbers because it's fun sometimes to have numbers. So I pump it up to 10 atmosphere, and I have a thermometer stuck in the output of the compressor, and it's saying my temperature is 350 Kelvin. So I try to map that. The pressure line, the constant pressure line on my TS diagram does this. I can draw that line because every combo of P and T has an S defined for it. So every time I have a P and a T, I could map out on this line where's the new S for each new T for each pressure. If I move around this space, I'm changing pressure and temperature and entropy. So here's my T2, let's call it actual, and this is T2. My notation here is S for isentropic and A for actual. Some textbooks use T2 and T2 dash. I prefer to use T2S and T2A because it lets me say the words isentropic and actual as I write them down. So I've got T2A here, S2A. I measure 350 Kelvin. I put it on my PV diagram, on my TS diagram, and I say, hang on a second. For that to be real, my entropy has gone up. For that to be the true new pressure and temperature, my entropy has to have gone up. Pressure gauges, I have. They're easy. Temperature gauges, thermometers, I have. They're easy. Those two tools have allowed me to work out, without knowing a single thing about what happened inside the compressor, how much energy, how much extra work it took to compress that gas because of the friction inside the system. So, the area under this graph is a heat transfer as well. There's something else going on. I could put that on a PV diagram and determine the reversible work that was required. But the important thing is I don't even need to do those maps. At this point here, I've got internal energy, I've got enthalpy. I could tell you something about the energy change required to get to that point. It's a compressor process, so work needed to be done to make it more compressed at a higher pressure. So I'm putting work into the system, and I've had to put more work in because of losses, and that extra work in has resulted in a hotter final temperature and a higher entropy. So the losses, all the losses in the system have been mapped by me being able to measure the state at point 1 and the state at point 2 actual. And I have a tool to evaluate now how far away from ideal I am, which also gives me an idea how much more improvement could I make on the system by better lubrication, better bearings, whatever. The other point of this slide in this lecture notes series is that this process from here to here and this process from here to here, this guy, we know isentropic equals adiabatic and reversible. Adiabatic we can see because there's no area under the TS diagram, so there's nothing to integrate to a Q. And reversible, we've shown. Now, this process from here to here, from T2 to T2A on a constant pressure increase in temperature A constant pressure, increase in temperature, also looks like this. A nice square box on a PV diagram is a reversible process. I didn't say it's adiabatic, but it's a reversible work process. So what I've done is this real process, this non-reversible process, I'm able to split into two reversible processes. One of them isentropic, one of them constant pressure. My experiment right now is not talking to the computer and discovering it doesn't respond. Be a nice computer. We turn off? There you go. If this becomes a thing, I'm going to apologise for the next 2 weeks of me talking baby talk to the computer. But if it's the only way I can get it to function on a Wednesday morning, so be it. So, we've got all of that. There's the sketch that I drew here. So, we've got adiabatic and reversible. These are the words of everything I've just said here. The combo of these two reversible processes means that I can now exactly map what's going on if I were inclined to. The other thing that occurs is that we can separate out the difference between the compression process and the heating process. So part of what happened was the isentropic compression, the adiabatic compression. Then part of what happened was an increase in temperature due to heat transfer that was got nothing to do with rises in pressure. So this way for you, this way and this way. Or changes in pressure, changes in temperature add up to this irreversible process here. If you are paying attention to the detail, this gets me to the same T2 or T2 actual, depending on your notation. So both of these get me to the same state, but you will be aware that they are different in that the heat transfer of this process, the area under this graph is different to the area under this graph. So I've been able to decompose it into things that I have tools for. I can map my way towards T2A, or if I have T2A measured, I can map my way back to be able to analyse the problem. But I do have to say that those two combos of processes are not absolutely, utterly identical. So before we go into gas mixing, the analysis of compressors and turbines with exactly that map, we do a lot of. I don't want to jump back onto the document capture just yet because I burned a bit of time getting on there. If I draw a turbine that is allowing gas to expand isentropically, I've got a pressure here. Wow, I've got a pressure here and a pressure here. Which way do I go on the temperature map? This is now the opposite of the compressor. The turbine is the opposite of the compressor. So I'm going from a high pressure to a low pressure, and isentropic, I go straight down. It's the opposite of a compressor. Now the real process, which way does entropy go? So that was the isentropic process. Which way does entropy go for the real process? It's the opposite of the compressor process. So it does that. This is you guys looking at the graph. Or this. I got some nodding. I got a little bit of positive feedback when I came this way, which is nice. And I got no positive feedback when I went this way, just a lot of blank faces, which I'm going to take as you saying, no, don't be silly, I couldn't do that, which is correct. The process results in an increase in entropy or no change in entropy, not a decrease in entropy. So the turbine is trying to let work out of the system, and as a result of the friction, the best possible work I could release is measured by the delta T. Imagine it's an ideal gas, Cp delta T. The best possible work I could let out of the system is to this temperature. This temperature is higher, which means a smaller delta T, which means less work out for the real process because of friction. In the compressor, Cp delta T is the amount of work in. So this guy is the smallest possible work for the compressor. And the higher temperature gives me a bigger delta T, which means more work required to compress. So the losses in the compressor and the turbine put together, the compressor was harder to run, so I had to put more work in to compress, and my turbine lets less work out because of the losses. So both sets of real processes result in a less efficient machine if they're connected. All right. Now we're going to do gas mixing. Drop my pen. Once again, two boxes separated by a partition. P, V, and T for substance 1, P, V, and T for substance 2. We've done this analysis on a first law basis. We've looked at what happens when I let them mix and that they reach some stable temperature because the internal energies are the same. I think there's even tutorial problems saying what's the final temperature or what's the final state of gas. I think our very first steam problem said take the partition out. So I think lecture 6, take the partition out and determine the final state. That was done on a first law basis. What I'd like to do with this guy now is have a look at the second law idea of what's happened to my entropy. So we're going to do a couple of things. One, we're going to make it an ideal gas, and we're going to make those two ideal gases, two gases that are unable to react with each other. So it's just, I'm just locking down all the possible things that could go on. Nitrogen and argon are not going to react with each other no matter what happens. And I'm going to set the temperature and the pressure to be the same. So the volumes are different between 1 and 2. T is the same, P is the same. And I'm going to take the partition out. Eventually, the two gases are completely mixed into each other. So we've set up our rules. We've got an ideal gas. We've set our temperature. We've set our pressure. We've got our volumes. We've got no mass crossing the system. So it's a closed boundary. And what we're now going to do is try to make a statement around what's happened to entropy here. So what we're going to do is keep track of the entropy of gas number 1, of substance 1, and the entropy changes of substance number 2, and see what they look like. I think this is a neat exercise. Because we haven't put any numbers in, lights. We're going to let time go to infinity so they're completely mixed. We've got the two boxes. We've got the box. So 1 had P, V1, T. 2 had P, V2, T. This is V1 plus V2. And we're going to say that P and T are the same at the end. So these temperatures on an ideal gas, if the temperatures are the same and then they all mix together, I get these guys are the same as what I started with. So on an energy basis, we don't feel like much has happened at all. And say V1, we're now interested in the specific volumes. What I'm going to keep track of here is what's happened to the specific volume of gas number 1 at the beginning and the end? And what's happened to the specific volume of gas number 2 at the beginning and the end? The masses cancel out. So here, if I write this down, my beginning volume for substance 1 is this volume, and my beginning volume for substance 2 is this volume. All the molecules now occupy a larger space. They're all completely diffused and interspersed. We're okay with that? V2, this was my initial volume, and at the end, I occupy the same volume. So the two masses are completely and utterly interspersed. I'm using gases, so I can allow the molecules to just be bouncing off each other and diffuse completely and utterly in between each other. Now this guy occupies the same new volume, and it's the same mass. I haven't changed. There was a closed system, so I haven't changed the mass at all of either substance. So the mass term cancels out here, and the mass term cancels out here, which means that my specific volume ratio looks like this, and my specific volume ratio looks like this. This gives us a hint that we're probably going to use our change in entropy rule that we derived for an ideal gas. We're going to use the version that had specific volumes in it rather than the version that had pressures in it. The version that had pressures in it was for enthalpy, is for systems where mass flows, where I've got mass crossing the system boundaries. The system with the specific volumes in it is for internal energy problems. And also, you pick up the tool that is most useful in solving the problem. So, that equation looked like this. Change in entropy equals CV log T2 on T1 plus R log V2 on V1. This guy here is what? Is it? What's the log of 1? This guy is 0. The temperature has stayed the same, so T2 on T1 is 1, the log of 1 is 0. So this term dies, and what I've got is that my entropy change for either substance is equal to R log V2 on V1. And I've made a statement for V2 and V1 for both substances. Yep. So what I've got now is that the delta S for substance 1 equals R1 log V on V1, and delta S for the other substance is R2. Remember I said argon and nitrogen, they're two different R's. Log V on V2. So, is V on V1 big, small, greater than 0, less than 0? Is V bigger than V1? Yes. What's the log of a positive number? Well, let's say what's the log of a number greater than 1 is greater than 1. So this guy is positive, and this guy is positive. Both substances have increased in entropy. So also for my system, each substance has increased in entropy, and my system has also increased in entropy. Because I haven't allowed any mass to cross the system, I've left it nicely insulated, my temperatures have stayed the same. I gave you no numbers. I gave you a mixing problem. I made it a relatively simple mixing problem because I said ideal gases and constant temperature, constant pressure. And in that really nice simple mixing problem, we have that entropy increases. I gave you a coffee cup filled with coffee with a mixed process, and your instinct told me it will never, ever, ever into infinity ever unmix itself because entropy has increased. This is the maths of why my coffee will not unmix itself. It's the maths of why we won't suddenly suffocate because all my oxygen's on one side of the room and all my nitrogen's on the other side of the room. And I happen to be unlucky 80% of the class in the nitrogen side. A mixing process is an increase in entropy. Okay, we'll wrap up this lecture. Nicely, everything. So, that's everything I just said, but it's on screen, so it's in the lecture capture. We're now done with setting up entropy as a problem, and so we're going to start to look at heat engines and how to use these tools and how to use the tools of reversible processes between states. How you doing? Okay, we'll talk outside because I need to get out of here.
Yeah, I have class because I'm very quick edition.
But literally, I need to pack up because this guy's standing right here to teach. So let's talk at the door. Good, much better, much better. This is actually behaving itself. So that's mine, these are yours, that doesn't work, I was going to throw it away somewhere. And you can have the microphone, you can use a microphone. There we go.